Okay, in lesson 3.4, we're going to be taking a look at something called concavity, and that's going to relate to second derivatives. Okay, so some new vocabulary that you're going to have to add to your growing list of new vocabulary, and that is concavity. So you can see from this little illustration here and the graph, or a piece of a graph below, we call that shape concave up. And if the little picture of a little teacup there kind of helps you remember that, concave up, I suppose, is a way you could describe like being able to hold a liquid or something along those lines. So that shape that you see right there is concave up. But how can we get more of a mathematical calculus-based definition for showing a graph that has the shape of concave up? Well, what we're going to do is we're going to take a look at the slopes of this shape from beginning to end, from our starting point, if you want to call it that, to our ending point. Back in 3.3, we would always look to the left and to the right of our critical point, which would have been down here at the bottom. But we don't really care about the critical point here. We're going to look at the slopes from the start of this curve to the end of this curve. So to start off, or to answer the question, again I'm posing, are the slopes of the tangent lines increasing or decreasing? But not to the left or to the right of the critical point, through the whole curve. So let's start with what we see at the beginning, if you want to call it that, of the curve on the left side of this curve. We know the slope is negative, just like we saw in 3.3. But since we're looking at the overall picture here, the overall slopes, you'll notice we're going from negative derivatives, or negative slope, to zero slope. So if you ever go from negative numbers to zero, that would be an increase. So our little concave up picture here is starting off with negative slope, but those slopes are increasing. They're increasing till we get to a zero slope. But that slope is still increasing. You'll notice after our zero slope, which again is where we have a critical point, our slopes then become positive. And they're still increasing more. As this concave up picture gets more and more steeper, those slopes are getting more and more positive. They're getting bigger and bigger and bigger. So we know that our derivative is starting off negative, it's coming to a zero slope, and then the derivative becomes positive. So if we look at this overall picture, we can observe that the slopes, or the derivative, is increasing. So what does that mean? Well, this might not be intuitive to you right now, but what that means concerning the second derivative is that the second derivative must be positive. And if you're kind of having trouble seeing that, you can jot this down somewhere on your notes. I didn't put it in this slideshow, but to kind of give you an analogy for why that's true, I'm going to use something that we already know. If I tell you a function is increasing, you know something about its first derivative. We know the first derivative is positive. So that's going to kind of be the observation we can make through this pattern I'm going to try to get you to see. So kind of erase what I just, well, don't erase it, but kind of pause that, so to speak, for a moment. What if I now tell you that f prime of x is increasing? Well, to kind of fill in this pattern, if I tell you a function's increasing, then we know the derivative after it is positive. So if we take that knowledge and apply it here, if I tell you a derivative is increasing, we can say that a second derivative is positive. And that's the main thing you have to see. To kind of continue this pattern, we'll never use this in this class, but just to make sure you're seeing this pattern, if I tell you a second derivative is increasing, then you can say what about the next derivative over, which is the third derivative? Well, we can say that that is positive. So if you ever see a function or a derivative increasing, you know the derivative after that is positive. So since we observed that the slopes or the derivatives are increasing throughout this concave up picture, we know the second derivative must be positive. And that's ultimately the conceptual understanding that you need to take away this fact. If I ever tell you a curve is concave up, you know the second derivative will be positive. So hopefully you understand the conceptual reasoning behind that, but ultimately this is the fact that you're going to have to remember. Okay, so of course we can kind of take the opposite viewpoint, and that's going to help us describe what is called concave down. I guess in that case we've spilled our little coffee cup there. So you'll notice that the slopes start off as positive, they go to a zero slope, and then they go to a negative slope. If we start off with positive numbers that go to 0, that go to negative numbers, we can see that those values are decreasing, or in other words, the slopes of the tangent lines are decreasing, which means the second derivative must be negative, or again, the fact ultimately that you're going to have to take away from all of this is that if your graph is concave down, you're going to have to remember that the second derivative is negative. One other thing concavity, concave up, and concave down leads us to is something called points of inflection. So first things first, quick review of that last slide. We see this first piece of our graph is concave down, which means the derivatives are decreasing. That's the concept. And on the right side of this graph, we see concave up, or in other words, the slopes are increasing, the derivative is increasing. The way we interpret that is for concave down, we know the second derivative is less than 0 or negative, and for concave up, our second derivative is positive or greater than 0. And you'll notice in this picture we have a junction, so to speak. We have a point where we went from concave down to concave up, and that is what we call a point of inflection, or an inflection point. And that's just a point where the graph changes concavity from either concave up to concave down, or concave down to concave up. The fact that you're going to have to take away from this is since right at that point we kind of have a neutral concavity, so to speak. At these inflection points, we're going to have to remember that the second derivative is 0 or undefined, kind of like a critical point. But we're using the second derivative to find these inflection points. But here's one big thing you're going to have to remember when we find these, or possibly find these inflection points. If you find where a second derivative is either 0 or undefined, all those points are candidates for being inflection points. Back in 3.3, when we were finding critical points, we knew for sure they were critical points. We just had to do some work to determine if they were relative maxes or relative mins. For these inflection points, all we can say is that they're candidates, and then we'll do some work to figure out if they are indeed inflection points. Okay, these first 3 examples I'm going to do in 3.4 are actually 3 examples we did back in 3.3. I'm just going to take them a step further and analyze their concavity, and then maybe use some of that information to, as you see here, to sketch the graph. Okay, so what did we learn back in 3.3 about this problem? Well, we took a first derivative, we found a critical point at -1/4. When we made our sign chart, we found that that -1/4 was a relative minimum. But now I want to take this one step further. I want to determine the concavity of this graph. And to determine concavity, you should always be thinking of second derivatives when you're talking about concave up or concave down. So we need a second derivative. Luckily, that's very, very simple here. Our second derivative is equal to 8. So what does that mean? Well, we just discovered that our second derivative is always the number 8, which is a positive number. back from that first slide, the little fact you need to remember, hopefully you understand the conceptual reasoning, but the little fact you need to remember is that if your second derivative is positive, you know your graph is concave up. And since this second derivative is always positive, it's just the number 8, we know this graph is always concave up. So the graph is concave up from negative infinity to infinity. But let's kind of back up and think about this equation for a moment. We know this equation is just a simple quadratic equation, which is a parabola. And of course, if we've defined the shape of concave up as what you saw on that first slide, then now we know why parabola looks the way it does. Combined with the first derivative test and now this concavity issue, we know why parabolas don't wiggle in between their points. They have to remain consistent in that they are always concave up if it happens to be a concave up parabola, and of course with our critical point being a minimum. It has to be decreasing to the left and increasing to the right. Okay, moving on to another example we did in 3.3. As a reminder, this is what we found from our first derivative test back in 3.3. We have a relative max at -1 and a relative minimum at 3. So now we want to again examine this new idea of concavity, which means we need to take a second derivative. And in this case, our second derivative is 6x minus 6. So how are we going to determine where this graph is concave up or concave down? Well, the way we did it back in 3.3, we're going to set up a sign chart. But before we set up that sign chart, we have to find some possible points of inflection. That's what's going to chop our graph up into the concave up or concave down pieces. So if you refer back to that slide from before about points of inflection occur where the second derivative is 0, and in this case that happens at x equals 1, and undefined. Well, there's really no point in checking for undefined here since 6x minus 6 is never undefined. But the major point we need to make here is that's not an inflection point. It's merely a candidate for being an inflection point. It may or may not be one in the end. So how are we going to determine if it is a point of inflection, and within that determine where this graph is concave up and concave down? Well, we're going to go to something you guys have been practicing now for at least one lesson. We need to set up a sign chart. And back in 3.3, I mentioned we need to label our sign charts so we know what kind of sign chart it is. And the major reason for that is now we have a different sign chart. This is a second derivative sign chart, so I'm going to label it as G double prime. Just like our sign charts in 3.3, we're only going to put our candidate for a point of inflection on the sign chart, no other numbers. Just like we did in 3.3, we need to pick a number to the left and to the right, and plug that now into the second derivative. This is our second derivative sign chart, so that's where we need to plug it into. Okay, so I'm going to take 0 to the left of 1 and plug it into my second derivative, and we're going to get a -6. We don't really care so much that we got 6, a -6, or the value of 6 as our answer. We care more that it's negative. To the right of 1, I'm going to pick 2. When you take 2 and plug it into the second derivative, you'll get +6. Again, we don't really care so much that the value is 6, more that the sign of it is positive. So back in 3.3, the way we kind of rounded out the labeling of this sign chart is we put an arrow up or down. Well, now that this is a second derivative sign chart, we don't want to put an arrow going up or down because that's not the way we interpret this sign chart. If we have a negative second derivative, we know that graph, or that piece of the graph, will be concave down. We don't label the positive with an arrow going up. It's a second derivative sign chart, so if it's positive, we label that with a concave up graph. So let's go ahead and talk about where this graph is concave up and concave down. From 1 to infinity, our graph of G is concave up. From negative infinity to 1, our graph of G is concave down. But now we can take that information and make a very important conclusion. We said x equals 1 was a candidate for being a point of inflection. So did it turn out to actually be a point of inflection? Well, we observed that our graph went from concave down to concave up. So we can conclude that that point x equals 1 is a point of inflection because the second derivative changed signs. Back in 3.3, if we had a relative max like we do over here, or a relative min like we do over here, we had to be specific. We had to say the first derivative changed from positive to negative or negative to positive. In these cases of inflection points, we really don't need to be specific if it changes from negative to positive or positive to negative. We just needed to observe that the second derivative did change signs. So that's how I'm going to word it and justify it in that manner. If you want to take a look at what this graph looks like, you'll notice that indeed we do have a point of inflection at 1 like we discovered. To the left of 1, our graph is concave down. To the right of 1, our graph is concave up, as you can see in the color coding of the graph. Okay, here's one more example that we did in 3.3, and again we're going to take this problem one step further to analyze the concavity. So we discovered that there was no max or min based on our first derivative sign chart. So we need to examine concavity, which means we need to take a second derivative. If you recall, back when we were trying to set our first derivative equal to 0, this is the version we wanted to use to set it equal to 0. Well, we kind of have to take that back a step because we don't really want to take the derivative of this to get to the second derivative. We want to take the derivative of that to get to the second derivative. Remember, we need it to be derivative friendly. So it's going to kind of be a juggle back and forth of which version of the derivative you might want to use depending on what you're trying to do. But ultimately, when you take that second derivative, you'll get negative 2/9 x to the negative 5/3. Just like with our first derivative, since we need to set this second derivative equal to 0, we don't want that negative power. So we're going to send that negative power of 5/3 down to the bottom of our fraction with that 9. And with that, it's a lot easier to set that equal to 0. So just like we've observed in many examples up until now, if we have fractions like this equal to 0, you'll notice that there are no x values when the second derivative is equal to 0. Again, if you want to look at it in a little bit different way, if you were to take the bottom and multiply it to the other side, we'd be essentially saying that 0 is equal to negative 2, which we know is not true. So you can look at it kind of either way, but ultimately there are no x values for when the second derivative is 0. But you can't forget, just like with the first derivative, we also need to check when the second derivative is undefined. Since we have a fraction for our second derivative, we need to take the bottom and set it equal to 0 because that's when a fraction is undefined. Here, there's really not math to do. That expression is equal to 0 when x is equal to 0. So again, that x equals 0 is not necessarily a point of inflection until we do our sign chart, so it's just a candidate for now. So let's jump into our second derivative again. Please label these sign charts so we know what kind of sign chart we're looking at. This second derivative sign chart will just have 0 on it. That is our candidate for a point of inflection. So if we pick a point to the left of 0, which I'm choosing to be negative 1, and evaluate that, we'll get 2/9. And again, we don't really care that the value is 2/9, we care that the sign is positive. If I plug in an easy point to the right, which will be 1 in this case, and evaluate the second derivative at that point, we'll find that we get negative 2/9. So I'll put negatives on the right side of our point, or candidate for point of inflection. Okay, so we need to round out this sign chart by interpreting it visually, I suppose. If we have positive second derivatives, we know our graph is concave up. If we have negative second derivatives, we know our graph is concave down. So let's go ahead and write down where we're concave up and concave down. h is concave up from negative infinity all the way up until 0. H is concave down, starting at 0, all the way to positive infinity. Next thing we can do is determine, did we actually end up with a point of inflection? And again, remember, for a point of inflection, we just need to see concavity change. It doesn't matter if it goes from positive to negative or negative to positive. In this case, our concavity is changing from positive to negative, but we don't need to be specific about that like we would have had to with relative maxes or relative mins. We can kind of just keep it simple as you see below there and just put x equals 0 is a point of inflection or an inflection point because the second derivative, h double prime, changes signs. And again, to kind of verify this, like the last example, I'll give you guys a picture here so you can see that, and you'll notice something. Concave up doesn't have to necessarily look like that nice pretty picture for concave up. That is concave up. Same thing for concave down. It doesn't have to necessarily look like the nice pretty picture that we've been drawing for concave up. It can look like that green portion of the graph. So you can see it checks out. We were supposed to be concave up to the left of 0, we are. We're supposed to be concave down to the right of 0, and we are, and right in between at 0 is our inflection point. Okay, we're going to shift gears just a little bit. We're still talking about this concept of a second derivative, but we're going to be looking at how it applies in this second derivative test. So make this little note here. It's not printed in the notes, but it's a big important thing that you need to realize about this second derivative test. It is only used to find relative extrema. In other words, this second derivative test is used only when we're trying to find relative maxes or mins. So you might be wondering, why would we want to do that when we already have our first derivative test from 3.3? Well, it might be useful to have a different method for finding relative extrema in certain problems. So that's why we need to take a look at the second derivative test. Okay, with that being said, now we can take a look at the details. So first thing we have here is that we're letting a point C be a critical number. And that's what's very important about this second derivative test, because in this first possible scenario, we're taking a critical point and plugging it in the second derivative. Please make note of that somewhere on the side in case you aren't sure what this is telling you. We're not just plugging in any random number into the second derivative, we're plugging in a critical point into the second derivative. And if we do that and find that the second derivative is positive, we know that critical point has to be a relative minimum. And you can see the visual of that here. We're not taking some point over here, over here, over here, over here, and plugging it in. We're plugging in a very important point into our second derivative, and that is a critical point. If your second derivative at a critical point is positive, which means concave up, then you have a relative minimum. So very important concept to kind of sort through in your heads. Of course, the opposite, I suppose, is true. If you take a critical point and plug it into the second derivative and get a negative value, which means concave down, we know that critical point must be a relative max. And again, you can see that visually right there. The only downside to this second derivative test is if you ever plug in these critical points into a second derivative and get 0 or undefined, all that you're going to be able to conclude from that is that the second derivative test failed, and you're going to have to go back to what we were doing back in 3.3 and use the first derivative test, which means do a sign chart and all those things. Okay, so that's what we're going to attempt to apply in this problem. We're going to use the second derivative test to find all the relative extrema, the maxes or the mins. I could use the first derivative test here, but I'm going to practice out this new second derivative test. Okay, so since this second derivative test needs us to plug in some critical points, let's find some critical points, which means we need to set our derivative equal to 0. And we'll get two values. We'll get 0 and 2. Normally here, we would set up our sign chart and pick all those numbers and figure things out. But we're not going to do that. We're going to apply the second derivative test, which says we need to take those critical points and plug them into the second derivative. So the second derivative is pretty easy to find here. It's just going to be 6x minus 6. Okay, so based on this second derivative test, to apply it, we take those critical points and plug them into the second derivative. So there's 2 critical points, so let's plug in both of those critical points. When we plug in 0 into our second derivative, we'll get negative 6. What can we conclude from that? Well, since our second derivative is negative, we know the graph is concave down. But please keep in mind, these 2 points here aren't just any old random points that we're picking. Those are critical points. And since that's a critical point and our graph is concave down, we know that we have a relative maximum at that point, which is x equals 0. Okay, same thing for our other critical point, which is 2. If you take the 2 and plug it into your second derivative, you'll get positive 6. The conclusion we can make from that, from this new lesson, is that our graph is concave up. But to apply the second derivative test, we have to realize that we just didn't plug in any random point into the second derivative. We plugged in a critical point. And since the graph is concave up, we know that critical point must be a relative minimum. Okay, last example is a very good example since it is an AP free response exam question. And just to make note of it, this is no calculator. So what do we have? Well, we have h as a function, and it's defined for all x values except at 0. So that might be important. They tell us we have a point, h of 4 equals negative 3, and they actually give us the derivative of h. We don't know what the function h is, but they give us the derivative, and you can see that the derivative is undefined at x equals 0, which you can clearly see right there since there's an x in the bottom. Okay, part A. We want to find all the x values for which the graph has a horizontal tangent. So how are we going to do that? Well, before we jump right into that part A, let's kind of label some of the info we were given above. If the function h is not defined at x equals 0, we know there's a vertical asymptote at 0, and that'll be very important in terms of interpreting whatever answers we're getting. The other thing you might want to do is, if you don't like this function notation, you might want to write the point they give you in its regular format of x, comma y, 4, comma negative 3. Okay, back to part A. We want to find all the values of x for which the graph of h has a horizontal tangent. Horizontal tangents happen, and I'll kind of point that out here. Horizontal tangents happen when our slope is equal to 0, or in other words, when our derivative is equal to 0. So we need to set our derivative equal to 0 and solve that equation. It's nice and simple. And since this is without a calculator, we're just going to leave our answer as plus minus the square root of 2. So we have horizontal tangents at positive square root of 2 and negative square root of 2. In case you were wondering roughly what that decimal is, it's about 1.4, but that's not actually a real answer. I just put that there so you can kind of see what that number is. Okay, so we need to take that information, the 2 horizontal tangents, which by the way are critical points. Those are critical points, and horizontal tangents, they're synonyms. And we need to determine where we have any local or local maximums or local minimums, or maybe they're nothing. And then we need to justify our answers. So keep in mind, if you're trying to find relative maxes or mins, we need to take critical points and put them on a sign chart to determine that. But we can't forget the case of when our derivative is equal to for when our derivative is undefined, and that happens when x equals 0. So don't forget that other case, because that will be a candidate for being a local max or a local min, even though we kind of already know, maybe you're realizing that there's a vertical asymptote there. So I guess it really doesn't count, but it is a critical point. So I'm going to put it on my sign chart to determine where we might have any relative maxes or mins. Okay, so we're trying to do this problem without a calculator. So we really don't need to know the specifics of the numbers we're getting. We again just need to know the signs of the numbers that we're getting. So since negative square root of 2 is roughly negative 1.4, a number to the left of that would be negative 2. If you take negative 2 and plug it into the derivative, you'll get a negative answer. In between negative square root of 2 and 0, I'm going to pick negative 1. If you take negative 1 and plug it into the first derivative, you'll get positive 1. And we just care that that number is positive. If we take a number between 0 and 1.4 and plug it in, which will be 1, and we're going to plug that into the first derivative, we'll get a negative answer. And if we choose a number after the square root of 2, which would be 2, we'll get a positive answer. Okay, so our goal is to determine if we have any relative maxes or mins. And you can see we have 2 relative mins. So we have to write that as a sentence since we need to justify our answer. There is a local minimum, or if you want to use the word relative, there are local minimums at x equals plus minus the square root of 2 because h prime changes from negative to positive. We know that there's no relative max at 0 because that's a vertical asymptote. So that kind of rounds out part A. Part B, which is why this example is in lesson 3.4, because now part B is talking about concave up. As soon as you see anything regarding concavity, concave up or concave down, I hope you're thinking about taking a second derivative. So since our first derivative is a fraction, I'll go ahead and apply the quotient rule. Again, if you need to pause and make sure you understand those steps, please do. But once you simplify the second derivative, which is really what we're trying to get after, you'll get x squared plus 2 over x squared. So normally, we would probably set that equal to 0, find the candidates for points of inflection, do the sign chart, but you can see I didn't really leave much space there to attempt all that. There's a little clever thing that you can do here to avoid having to do that analysis, and that is this. We don't need a sign chart because I notice something. I notice that when x is positive, the second derivative is always positive. If you plug in an x value and square it and add 2 to that, that's positive. And then we'd be dividing by a positive answer. So if x was positive, the second derivative would just be positive. And the same thing can be said for when x is negative. If you take a negative number and square it, that's positive. If you add 2 to that, that's still positive. And in the bottom, you'll take a negative number and square it, which is still positive. So if x is negative, the second derivative is positive. So it's something that it's maybe hard to identify when you can kind of cheat, if you want to call it that, and do a problem that way. But definitely, if you can do that, I would look at a problem that way. So we don't need a sign chart because we just discovered that the second derivative is always positive. So we can say the function h is concave up for all x values. So I suppose you could have put negative infinity to infinity, but you would have made a mistake of forgetting that we have a vertical asymptote at 0, so we have to put in there except at x equals 0. H is concave up for all x values except x equals 0. Okay, last part of this example is to write an equation of a tangent line. I don't want you guys to forget that little skill. It's something you'll be doing this entire year. So just as a quick reminder, if you see the words equation of a tangent line, you should be thinking y minus y1 equals m times x minus x1. So what does that mean? Well, we need a point and a slope. They tell us in part C we're trying to write a tangent line at 4, so we already know our point is 4, negative 3. So we just need to focus on the slope. How are we going to find the slope at x equals 4? Well, we need to take our derivative and plug in 4. Don't forget about that simple concept that we've known for some time now. If you plug in 4 into your first derivative, you'll get 7 over 2. And just like that, part C of this problem is extremely simple. I again want to remind you that on the AP test free response portion, you are more than welcome to leave your answers unsimplified, just like you see that I did here. I'm just going to take the steps for the practice of it to simplify it, but I want to point out this answer right here is perfectly acceptable.